Hello everyone, my name is Emanuele Giuseppe Esposito, and in this presentation we will show you how we can leverage cloud bursting to run a GPU-powered AI workload from an on-prem cluster that has no GPU. Let's start with the problem. Nowadays, GPUs are crucial for AI inference. However, an AI model can experience a different volume of requests over time, and this could depend on systemic growth, if the model is gradually gaining popularity and therefore queried more over time, seasonal peaks, when the model has much higher volume of requests than usual for a very short and sporadic amount of times. The same applies to GPUs. But what to do if our cluster doesn't have them? For example, the model is initially running on CPU, and over time, as the requests gradually grow, we decide to switch to GPUs. Or what about the cluster not having enough GPUs? There might be a peak of requests and a single GPU is not enough to cope with them. So how do we solve this issue? The easy option is to buy a GPU. However, we then need to wait that it gets delivered, pay for maintenance, and replace when obsolete. Would it make sense if the new GPU is not really used much, for example, only twice a year? The second option is to safely scale into the cloud. And this is what confidential cloud bursting is about, as we are about to see. Let's start with our typical setup. Our on-prem cluster capable of running traditional pods, but not equipped with GPUs. Let's introduce the public cloud. The cloud offers instances with GPUs. How we can leverage such instances to easily run AI models without moving the whole cluster into the cloud? Here is where the magic happens. Using confidential containers, we are able to run a single pod into the cloud. But how is this possible? This is possible because the pod actually runs in a confidential virtual machine, in short, CVM, into the cloud. From the OpenShift's perspective, in fact, a confidential container is no different from any other pod. What makes this confidential virtual machine so special in terms of security? The answer is the hardware and software behind it, which ensures data in use protection in addition to the traditional data at rest and in transit mechanisms. A confidential VM leverages confidential CPUs and GPUs to make sure that the memory of the CVM is encrypted and not accessible to the cloud provider. Once again, using confidential containers, we can safely burst into the cloud without trusting the cloud provider. We are not setting a cluster or a worker node into the cloud, but just a temporary virtual machine, which will die the moment the confidential pod stops. We pay only for what we are using, so not fixed costs in cloud. And to conclude, always have the latest GPU or hardware immediately available. No need of taking care of maintenance or upgrading it. But why do we need confidential containers for bursting? What security benefits do they bring? First of all, thanks to the PeerPods technology, a confidential container is capable of running as a standalone pod in a CVM outside of the on-prem cluster, even on an external cloud. Then, a confidential container does not allow anyone to inspect its workload or logs. A platform admin cannot exec into the pod. A platform provider admin cannot inspect the container memory dumps, as they are encrypted by the hardware. And of course, it cannot enter inside the CVM. Lastly, thanks to attestation, the confidential container will not run correctly if the remote attester, a program running in a secure environment, doesn't ensure that both the hardware and software have not been tampered with. Let's now look at the demo of our on-prem cluster not equipped with GPUs, bursting into the cloud. In this on-prem cluster, we can see that there are two deployments, vllm GPU, which tries to run the GPU locally, and vllm GPU remote, which tries to run the model on the cloud. Both deployments are scaled to 0. The pods are exactly the same. In the vllm GPU, we have an init container called download model, which takes care of downloading the Llama 4 Scout 17B from Hugging Face into our local folder. And then we have the main container, which requires a GPU because it runs the model via vllm. On the other side, the vllm GPU remote deployment has tiny differences. First of all, notice the annotation requiring the GPU. Then the init container is exactly the same as the other deployment. One major difference is the runtime class name, which for this setup is set to kata remote as we are bursting into the cloud. And to conclude, we have the main container, which runs vllm. Let's start by running the vllm GPU deployment. Notice how the pod is stuck into pending state because the GPU is not present in this on-prem cluster. Let's now run instead the remote pod. Notice how this container is actually running, but on an Azure confidential virtual machine, not on the on-prem cluster. On the bottom right corner, we can see the instance type is NCC ADS H100. First of all, the init container downloads the model from Hugging Face. And then the main container first detects CUDA and therefore the NVIDIA confidential GPU, and then starts the vllm server. Checking the Azure documentation, we can confirm that this pod is running in a confidential virtual machine using confidential CPUs and confidential NVIDIA GPUs. And now let's query our model. As it is now running, we are able to see it exposed in our Open Web UI interface. So let's select it and interact with it. To conclude, in this demo, we have shown you how OpenShift confidential containers work, what cloud bursting is, and how does it work to scale securely and dynamically into the cloud, and cost-effectively leverage missing resources like GPUs from the cloud. This concludes our presentation. Thank you and goodbye.